So the first module is differential amplifier. Differential amplifier consists of two transistors which share similar electrical properties, and when two transistors share similar electrical properties, you call it as matched. So Q1 and Q2 here are matched. That is, even if there are uh, many transistors with the same make by the same manufacturer, they may not share ideally equal electrical properties. So if they share ideal electrical properties, they are said to be matched. Equal electrical properties, they are said to be matched. So here Q1 and Q2 are NPN transistors, and they are assumed to be perfectly matched in the ideal situation. So Q1 and Q2 have uh, a collector resistor, and these collector resistors are also assumed to be of the same value, same tolerance, same value, everything. So these two transistors have their emitters shorted, and you have a tail current I, okay, flowing through the emitter of these two transistors, and this is minus VEE, and you have two base voltages VB1 and VB2 connected to either of the transistors. The collector voltages are called as VC1 and VC2. So first of all, we assume that Q1 and Q2 are matched, RC are same, VC1 and VC2 are the collector voltages, VB1 and VB2 are the base voltages, I is the tail current, and here you have minus VE. So in this case, first case, we are assuming that VB1 is equal to VB2. When VB1 is equal to VB2, then you call it as a common mode. That is, the differential amplifier is said to be in the common mode when both the inputs are same. So in this particular situation, we are going to prove that V naught, you can see the polarity of V naught assumed here, that is Vc1 minus Vc2 is equal to V naught. So we have taken the polarity like this. If you take the polarity in the opposite form, that is here plus and here minus, then it will be Vc2 minus Vc1. So in this particular case, V naught is taken as Vc1 minus Vc2 because of this polarity. So we are going to prove that in the common mode, a differential amplifier rejects the common signals. That is, when a common signal is given to the base of both the transistors, then V naught is equal to 0. This is what we are going to prove. So in this particular case, uh, VB1 is equal to VB2. So when VB1 is equal to VB2, we have to find out what is IE1 and IE2 when in relation with I. So in this particular node, you can see that IE1 is entering this node, IE2 is entering this node, and I is leaving the node. So that by KCL, IE1 is equal to, IE1 plus IE2 is equal to I. So in the normal case, not in the case of VB1 equal to VB2, in the normal case, in this particular node, IE1 plus IE2 equal to I by KCL. So in this particular case, when VB1 equal to VB2, both the transistors are assumed to be on, that is VB1 and VB2 are sufficiently large so as to keep Q1 and Q2 as on. So when Q1 and Q2 are both conducting, you will have IE1 and IE2 flowing through the emitters of these two transistors. So by the KCL, IE1 plus IE2 equal to I. So when IE1 is equal to IE2, why is IE1 equal to IE2? Because both the half circuits are similar. One is the mirror image of the other. So the currents flowing through each of the branch will be equal. So that IE1 equal to IE2. Henceforth, IE1 equal to I by 2 and IE2 equal to I by 2, since IE1 equal to IE2. So I by 2 will flow through Q1 and I by 2 will flow through Q2. IE1 equal to IE2 equal to I by 2. So when I by 2 and I by 2 is flowing through Q1 and Q2 emitters, what is IC1 and IC2? IC1 is actually alpha at times IE1 and IC2 is alpha times IE2. In this particular case, I am assuming that alpha is approximately equal to 1. So when alpha is approximately equal to 1, you can say that IC1 equal to IE1, which is in turn equal to I by 2. And IC2 equal to IE2, which is in turn equal to I by 2. So IC1 equal to IC2 equal to I by 2. Next, we have to find VC1 and VC2 to find V0. So VC1 equal to VC2, that is equal to VCC minus the current I by 2 flowing through the resistor into RC. And since these two currents are same, the voltage across the resistors are also same. Voltage across the resistors are I by 2 into RC. So VC1 equal to VCC minus I by 2 into RC and VC2 equal to VCC minus I by 2 into RC. So V0 is VC1 minus VC2, which is equal to 0. Since both the voltages are same, there is no potential difference between the collectors of these two transistors and hence V0 equal to 0. Hence we prove that during common mode signals, when common mode signals are applied to a differential amplifier, it will be rejected. So this is the first case. Now the second case is when VB1 is plus 1 volt and VB2 is 0 volt. VB1 is greater than VB2. VB1 greater than VB2, wherein VB1 is sufficiently large. So when in the case of a differential amplifier, it is not like in the case of a standalone transistor. In the case of a standalone transistor, we say that a transistor is on and working and conducting current when the base emitter voltage of that particular transistor is equal to 0.7. So the base is 0.7 volt greater than, more positive than its emitter. Only then an NPN transistor is said to be on or conducting. If this is not the case, then that particular transistor is off. But in the case of a differential amplifier, there is a slight change. In the case of a differential amplifier, a particular transistor is said to be on and conducting when the difference between the voltages of the two transistors in the differential amplifier is sufficiently large. So in this case, The difference between the input voltages of these two transistors is 1 volt. That is, we are taking it as this minus this. So 1 minus 0, it is 1 volt. So this is, when compared to a differential amplifier, 1 volt is a very high value, because in differential amplifiers, if the difference is in the millivolt range itself, one of the transistors or two of the transistors will be working in the on condition. So 1 volt is sufficiently large. So you can say that one of the transistors is on. Which is on? The one with more positive voltage. Why more positive voltage? Because these are NPN transistors. So which is the transistor that is on? The transistor that is on is the one with more positive voltage at its base. So VB1 is more positive in this case than VB2. VB2 is in the ground potential. If this was also a positive value, a value greater than 0, or maybe nearer to 1 volt, then both will be on. In this particular case, this is 0 and this is 1. So Q1 will be on and Q2 will be off. So Q1 will be on and Q2 will be off. So we have to prove that Q2 is off, Q1 is on as, okay. It is very clear, because this is a voltage greater than 0.7 volt, which is the minimum voltage that should be applied to the base emitter. So Q1 is on. So we should know the emitter voltage. In order to find the base emitter voltage of Q2, to find out whether Q2 is on or not. So in order to find the emitter voltage, we have to first find out what is the base emitter voltage of Q1. Since Q1 is on, base emitter voltage of Q1 will be 0.7. So base emitter voltage of Q1 is 0.7, and we are for now assuming that minus VEE is at ground potential for ease of explaining. So this is 1 volt, this is 0.7 volt. So now if you are taking the KVL in this branch, in this particular loop, you can say that it is 1 minus VBE minus VE. VE is the voltage at this particular point with respect to ground. So 1 minus VBE minus VE equal to 0. So 1 minus 0.7 minus VE equal to 0. So VE equal to 1 minus 0.7, that is 0.3. So the voltage at this particular point is 0.3. VE is 0.3. So what is VBE of Q2? VBE of Q2 is VB minus VE. That is 0 minus 0.3. That is minus 0.3. Voltage at the base with respect to emitter is voltage at the base minus voltage at the emitter. Voltage at the emitter is 0.3. Voltage at the base is 0. So 0 minus 0.3 is minus 0.3. When minus 0.3 volt is applied to the base emitter of Q2, Q2 is naturally on because it's a NPN transistor. So Q2 is off, Q1 is on. When Q1 is on, Q2 is off. By the previous from the previous circuit, we had proved that IE1 plus IE2 equal to I. Here IE2 is 0 because Q2 is on. So IE1 equal to I. So the entire current I will flow through the transistor Q1 alone, and no current will flow through Q2. So that is what is explained here. Q1 is on and Q2 is off. Entire current will flow through I. Q1, and the rest, no current will flow through Q2. Here this is the 0.3 volt at the emitter. Now when this is I and this is 0, through this particular branch there is no current through Q2. So what is the current through RC? Here we are taking alpha also. So current through RC will be alpha into I. That is IC equal to alpha into I. So what is VC1? VC1 is VCC minus alpha into I into RC. And VC2 is VCC minus 0. Why 0? Because I is 0. So VCC minus alpha I, alpha I into RC. I is 0. So VCC minus 0. Here you have VCC. Here you have VCC minus alpha I into RC. So what is V naught for this particular polarity? VC1 minus VC2. So this is alpha I, this is 0. We found out the voltages at VC1 and VC2, and this is VCC minus alpha I into RC, and this is VCC. So difference will give you the V naught. So V naught equal to VC1 minus VC2, and that is VCC minus alpha I into RC minus VCC, that is minus alpha I into RC. So which is this particular case? When VB1 is greater than VB2, and in that case you have a negative sign at the output. This is the case when you are taking V naught with this particular polarity. Okay, so when VB1 is greater than VB2, the V naught will have a negative value, that is input and output are out of phase by 180 degree. That is the significance of this particular negative value. So why is it negative? Because VB1 is greater than VB2. So in the case of an op amp, the differential amplifier is the first stage of an op amp. So in that particular case, this particular base is taken as the inverting terminal, and this particular base is taken as the non-inverting terminal. So if we reverse the inputs, that is VB1 equal to 0 and VB2 equal to plus 1 volt. Third case. In that case, the entire thing will reverse. That is, Q1 will be off, Q2 will be on. Q1 off, Q2 on means current will flow entirely through Q2. No current will flow through Q1. So here we will have 0, and here we will have alpha I, and VC1 will be VCC, and VC2 will be VCC minus alpha I into RC. So what will be V naught? V naught will be again VC1 minus VC2 itself. So that will be VCC minus VCC minus alpha I into RC, and the output will be alpha I into RC. So we can see that here we have a negative sign, here we don't have the negative sign. Why? Because in the second case VB1 is greater than VB2, and in the third case VB1 is less than VB2. So hence we can say that if V0 is taken with this particular polarity, then the base of Q1 is the inverting terminal and base of Q2 is the non-inverting terminal. So there is no phase shift between the difference of the input and the output in the third case, because the inverting terminal voltage is greater than non-inverting terminal voltage. If you consider this particular case, the differential amplifier as the first stage of an op-amp. Now, next case is when VB1 is minus 1 volt and VB2 is 0. So as I previously said, there is a difference in the working of a transistor when a transistor will be switched on or off when you're considering the transistor as a standalone transistor and when you use the same transistor in a differential amplifier. So if the difference is sufficiently large, then one of the transistors or both of the transistors will be on. It needn't necessarily be that individual transistor has sufficient positive value at its base. So that is, this particular case is that is, in this case Q1 has a base voltage of minus 1 volt and Q2 has a base voltage of 0. So normally we say that both the transistors should be off. But when these two transistors are part of a differential amplifier, the difference is taken and the difference is 1 volt. So since the difference is 1 volt, one of difference when you are taking, you take the modulus. You don't take this minus this, you take the modulus. So modulus of minus 1 minus 0. So difference is 1 volt. So if the difference is 1 volt, you can say that since 1 volt is sufficiently large and you need just in the order of millivolt or ideally in the order of microvolt, the difference between the input voltages. Here one of the transistors is on. So which transistor is on? Whichever transistor has a positive voltage, base voltage or a higher base voltage, that will be on. So here 0 is more positive than minus 1 volt. So Q2 will be on and Q1 will be off. So the remaining everything is similar to the previous cases. Q2 is on and Q1 is off. So we can prove that when Q2 is on, because the base voltage is sufficiently more positive than minus 1 volt. That is, it is 1 volt more positive than the base voltage of Q2. VB2 is 1 volt more positive than the base voltage of Q2. So then let's find the emitter voltage of these transistors so as to find the base emitter voltage of Q1. Thereby we can find out whether Q1 is really on or off. So when Q2 is on, base emitter voltage will say that it is 0.7 volt. So VB minus VE is 0.7 volt. In all these cases, VEE minus VEE is taken as 0. So VB minus VE is equal to 0.7. VB is 0. So 0 minus VE is equal to 0.7. So VE equal to 0.7 volt. VB equal to VB minus VE. VBE is zero point 0.7 and VB is 0. So 0 minus VE. So VE is, sorry, minus 0.7. So VE is minus 0.7. So here we have minus 0.7. Here we have minus 1. So what is VBE of Q1? Minus 1 minus 0.7 minus 1 minus minus 0.7, sorry, minus 1 minus minus 0.7 minus 1 minus of minus 0.7. So minus 1 plus 0.7. So that is minus 0.3. So Q1 is off. So since Q1 is off and Q2 is on, entire current will flow through Q2. We have VCC as VC1 and VCC minus alpha I into RC as VC2. These are repetitions of the earlier cases. We just need to find out which transistor is on or off and how. So V naught equal to VC1 minus VC2. So that is equal to alpha I into RC. So here by this particular case, we prove that each individual base voltage needn't be greater than 0.7 for the transistor to turn on. The only requirement is that the difference, modulus of the difference between the two input voltages should be sufficiently large. What is sufficiently large? That depends on each differential amplifier, how you design it. So we can say that if it is greater than a particular millivolt range, if it is in the volt range, that is sufficiently large. It will be normally designed in the millivolt range. That is called as sensitivity of the differential amplifier. We won't deal with it right now. So if it is greater than a few millivolt of millivolt, few millivolts, then one or both of the transistors will be on. In this case, it is negative volt. So we can very conveniently say that Q2 is off. And we even proved it by assuming that Q2 is on. We know that Q2 is on because it is 1 volt. Its base is plus 1 volt more than the base voltage of VB1. So Q2 is on, you know. So we find the emitter voltage. Thereby we'll find the base emitter voltage of Q1. So thereby we prove that Q1 is off because the base emitter voltage is minus 0.3. Then rest is like in the previous cases. So these are the 4 cases. First case is common mode. The signals will be rejected. Second case is VB1 greater than VB2, where VB1 is a positive value and VB2 is such that that particular transistor is off. Next case is when VB1 is less than VB2 and the second transistor is on and first transistor is completely off. Now, fourth case is when both the voltages are individually less than 0.7 volt, but one of the transistors is on. Now, suppose if both the voltages are sufficiently large to turn on both the transistors, but both the voltages are positive. Okay, VB1 and VB2 are both positive, but not same. First case was VB1 and VB2 were both positive, but both were equal. We can also consider the case wherein both are not equal, but both are positive. In that case also, both the transistors will be on, but the currents will be different. So how will the currents be different? Whichever transistor has a higher base voltage, more current will flow through that transistor, and comparatively lesser current will flow through the other transistor. Maybe delta I, that is I plus delta I, sorry, I plus delta I will flow through one transistor, and I minus delta I will flow through the other transistor. Delta I is the difference between the currents of both the transistors. So likewise, if you know the inputs of both Q1 and Q2, you can say that whether uh, each transistor is on or off. You can find it uh, using the emitter voltage, and if you know the know whether each of the transistors is on or off, you can find IE1 and IE2, you can find IC1 and IC2, thereby you can find VC1 and VC2, and henceforth you can find V0. Now this is a question, a problem. In this particular problem, you have Q1 and Q2, both are PNP transistors. In the earlier case, Q1 and Q2 were NPN transistors. So since these are PNP transistors, there is a slight difference in the circuit. Here VEE, minus VEE is considered. It is not ground, it is minus 5 volt. So in this particular case, find VE. VE means voltage at this point with respect to ground. VC1 is the voltage at this particular point with respect to ground. VC2 is the voltage at this particular point with respect to ground. In the circuit of this particular figure, assume that modulus of VBE of a conducting transistor is approximately 0.7. Why modulus? Because for a PNP transistor, it is actually minus 0.7. For an NPN transistor, it is plus 0.7. What do you mean by plus 0.7 minus 0.7? That is, base is more positive than emitter by a value of 0.7 in the case of an NPN transistor, and base is more negative with respect to emitter in the case of a PNP transistor. NPN transistor base is more positive than emitter, and PNP transistor base is more negative than emitter, and the value is 0.7. So in this case, it will be minus plus is already put there. So this is PNP. So we have to find out which transistor is on. So in the case of a PNP transistor, as we already said, the base should be at a potential lower than the emitter for the transistor to be on. So we'll find out which transistor is on. So in the first case, Q1, base is at a voltage 0.5 plus 0.5. In the second case, base is at a voltage 0. So comparatively, Q2, base of Q2 is minus 0.5 lesser than the base of Q1. So the lesser the voltage, the transistor is on. Just the reverse of the earlier cases when you used the NPN transistor. So Q2 is naturally on. So Q2 is on means the base emitter voltage will be minus 0.7. It is actually minus 0.7. 0.7 with a polarity like this. So it is base emitter voltage is actually minus 0.7. So it is minus 0.7. So we have to find out VE. So what is VE? VE is the voltage at the emitter with respect to ground. Where is ground? Ground is at the base. So VE is actually minus VBE. So what is VBE? VBE is this and VE is this, just the opposite direction. So VE equal to 0.7. It is actually VBE of Q2 is minus 0.7 and VE is equal to minus of VBE, so that is equal to 0.7. This is actually okay, VBE with a polarity this. So VE equal to 0.7. Okay, so VE we got. Next is VC1 and VC2. Now what is VC1 and VC2? So in order to find out VC1, we know that Q1 is off and Q2 is on. So since Q1 is Q1 is off, there is no current flowing through this particular branch. So VC1, this KVL in this particular path, KVL in this particular path will be VC1. Here no current, so no drop across this resistor, plus 5 equal to 0. VC1 plus 5 equal to 0. So VC1 equal to minus 5 volt. Now in the next case, here we have a current because Q2 is on. Here we have a current. Here also we are taking alpha equal to 1. So same current flows through emitter and collector. So first we have to find out the current value in order to find out VC2. So what is current? VC2, right? VC2 minus 5 volt by the resistor value. VC2 minus 5 volt by the resistor will be your IC2. IC2 is here I. So IC2 or IE2 both are equal. So this is your IC2. So IE2 is also equal to this IC2. So what is IE2? That is 5 minus VE. VE is 0.7. So 5 minus 0.7 by this resistor 1K. So we get it as 4.3 milliampere. So this same current is IC2. Since these two are I because alpha equal to 1. So IC2 equal to 4.3 milliampere, that is equal to VC2 plus 5 by 1K. So by solving, we find out that VC2 equal to minus 0.7 volt. So this is the end of this particular lecture.